So let's talk about the axiom of choice. So that says given any element of any collection of non-empty sets, it's possible to select one element from each set. So the example that I just gave in the previous video, it seems to make sense, but that was for finite numbers, for finite sets. What happens if we're working with an infinite collection of sets? So one of the best examples to try to realize why the axiom of choice is really valuable is if we look at certain situations. So let's say, for instance, I have some sneakers. So if I have these are going to be real rough looking sneakers here. So if I have pairs of sneakers here, okay, so here's going to be one pair, and then I can form a whole bunch of other pairs of, say, sneakers. Then I'm going to have an infinite number of pairs of sneakers. So we're going to call this some type of infinite set. Okay, now instead of sneakers, what happens if I just simply look at socks? So what if I define a pair of socks here? So I have one pair of socks, I have another pair of socks, and so on and so forth. So again, I'm going to have an infinite collection of both of these socks. So I have infinite pairs of sneakers, infinite pairs of socks. Now, if I was to say, is it possible to choose one element from each of these sets? So we're taking each of these, we can consider like a set of sneakers, and we could consider these a set of socks. Is it possible to pick an element from each of these pairs? Now, you're thinking yes, right? I could just easily pick one from each of those, and that's fine. However, you can do it with sneakers here. So if these are sneakers and these are socks, it is possible to do this without the axiom of choice. Because what we could do is I simply pick the right shoe. Now, because there is a difference between a pairs of shoes, right? A right shoe is going to be different than a left shoe. I just simply define, I'm going to always pick the right shoe. And great, I'm able to pick one element from every set, but this doesn't need the axiom of choice. However, if I want to do the same thing with all of my pairs of socks, what I need is I actually need the axiom of choice. What the axiom of choice is saying is that there is what's called a choose function, this ability to pick something from each of these infinite pairs of sets. I can't always do that unless I could clearly define my choice. But because, remember, with socks, maybe you've never noticed before, but most people, there's not a difference between a right and a left sock. So my right is equal to my left when it comes to socks. So we can't tell the difference between these two socks. So how could I tell somebody which sock to pick from each of these? So to be able to pick one sock from each of these sets, I need the axiom of choice to be true. So this is usually why the axiom of choice, this is often seen as necessary. Because if I can pick my shoes, I should be able to pick my socks, right? So it just makes sense. So this is one of the arguments where people are like, yes, obviously I should be able to pick my socks, so I want the axiom of choice to be true. However, one of the main reasons why mathematicians are very scared or very opposed to the axiom of choice is what's called the Banach-Tarski paradox. So you can watch a whole bunch of videos on this, super fascinating, but the idea behind the Banach-Tarski paradox is that if I have a sphere, then what I can do is I can break up the sphere into a finite number of pieces. So a sphere is just the outside, okay, just the outside, not a filled thing. But I'm going to break up the sphere into a finite number of pieces. And what you need is you need at least 5 pieces. I think I don't think you can do this with 4, but I think if you have 5 or more pieces that you break this up into, you can do this. Okay, so you take a sphere, imagine breaking it up into 5 different pieces. So you have these weird little chunklets that all together will form a sphere. Okay, now what the axiom of choice allows us to do, so if we use the axiom of choice, what's going to happen, magic happens, and what I get, is I'm going to get 2 spheres, each one being identical to the original. So I take a sphere, break it up, reform it. I now get 2 spheres that are identical to the original one. So all of a sudden I have one that just magically creates a second one. So this is why it feels like magic, right? This is what a magician does. You can turn one thing into 2. So this axiom of choice allows us to turn one sphere into 2 identical spheres. So then obviously if I did the axiom of choice again, I could then be able to get 4 spheres if I wanted to, that are all identical to this original sphere. And so it's just multiplying without any reason. You have the same amount of material. And so this is why people all of a sudden are like, eek, no thank you, I don't like the axiom of choice, because I don't want the Banach-Tarski paradox to actually seem to be true. It doesn't seem like that should make sense. So this is why the axiom of choice has been historically very controversial. But as we set up here, it's also very necessary. There's a whole lot of mathematical theorems here that this is used for. A lot of them are outside of the scope of this class, but things that you want to be true in mathematics, if you don't have the axiom of choice, they're either impossible or very difficult to try to prove. So this is why the axiom of choice, we like it. But then down here, Banach-Tarski paradox is why we don't like it. But yet, again, this is now looking at the foundation of mathematics, that there's a whole bunch of controversy behind what we are assuming to be the foundation of our mathematics. Now, the last thing I want to discuss about all of this is that if you look at the remainder of the Zermelo-Fraenkel axioms, what's very unique about these axioms is, first off, the goal is that they should not contradict one another. So if this is our foundation of mathematics, these axiom systems, one key thing is that they should not contradict one another. If there ever was a contradiction, then this basically falls apart. Then with a contradiction, we're trying to prove things either true or false, but we're then trying to prove things that are false that are actually now true. So we don't want to deal with contradictions. So at this point, there are no contradictions in these Zermelo-Fraenkel axioms. But this is both with and without the axiom of choice. So with the axiom of choice, there's no contradictions. Without the axiom of choice, there's no contradictions based off of things true, the idea of a contradiction showing something's false or true, but trying to show something like simultaneously true and false. We don't have any of that. But what also is very unique about the axiom of choice is that the axiom of choice is independent of the other axioms. So remember, we talked about this with the continuum hypothesis, that it's independent of the axioms that we have, is that we can't prove it to be true and we can't prove it to be false. So the axiom of choice is independent. So whether or not you believe it or you don't believe the axiom of choice is true, it doesn't matter. It's going to be independent. We won't be able to get a contradiction. We won't be able to prove that the axiom of choice is true, nor could we prove that the axiom of choice is false. So it's independent of the other axioms. So you get to choose, which is kind of funny here. The axiom of choice allows you to choose if you believe the axiom of choice is true or not, because it's independent of all of the axioms. So this hopefully sheds a little bit of light on what the foundations of mathematics is at this point, after we went through this period of trying to deconstruct mathematics to have a rigorous foundation. But the key of all of this is that logic. This idea of logic is playing the leading role behind all of mathematics, that mathematics is trying to be based upon logical reasoning, that up here we try to figure out, are these axioms, are these logical or are they not logical, and do we have some type of intuition to believe that they're true, and again, trying to figure out, do they contradict one another? If we ever found a contradiction, we'd have to find a new set of axioms, but it doesn't look like at any point we will have a contradiction with these axioms.